Bismillahirrahmanirrahim. We continue our discussion on number system. In today's discussion, we will be talking on conversion for octal number system. As we had discussed in previous lectures, that there are total number of 12 different conversions, and we have done so far 7 number system conversions that include a total of 3 conversions for decimal number, such as decimal to binary conversion, decimal to octal conversion, and decimal to hexadecimal conversion. That makes a total of 3 conversions for decimal number system. Then we have also completed 3 conversions for binary number system that include binary to decimal conversion, binary to octal conversion, and binary to hexadecimal conversion. That makes a total of 3 conversions for binary number system. So collectively 6 conversions are completed. And then in previous lecture we started octal number system conversions, and we have done octal to decimal number system conversion. We will continue the octal number system conversion in today's lecture as well. Octal to decimal number system has been completed in previous lecture. That makes a total of 7 number system conversions being completed so far. So let's proceed with our discussion topic and see how we can convert an octal number to a binary number system. As I just mentioned, that we are working on number system conversions. Number system conversion is an important topic because everything that is being entered in computer is ultimately converted to a specific number system, and that is binary number system. So normally user enters in decimal number system, but it is translated in or converted in binary number system. Similarly, the memory system or the memory organization in computer is generally done using either hexadecimal number system or octal number system. So whenever we refer some memory location, so that is either in hexadecimal or in octal, so that has to be converted into binary number system. So this is the reason number conversion is an important topic, and you all must understand how we can convert one number system in another number system. In today's discussion, we are going to talk on how we can convert octal number system in binary number system. We had started octal number system conversion from previous lecture, where we had converted octal to decimal number system, and today we are going to perform another conversion for octal number, and that is octal to binary number system. So let's proceed with the methods and techniques how we can perform this type of conversion. Octal number system, as I just said, and we had already discussed it, what is an octal number system and what are its applications in previous lectures. Octal number system consists of total 8 digits that include 0 to 7 digit, collectively making 8 digits. It is commonly used to represent memory addresses in computers, and mainly they were used in mainframe computers. But this representation has now been replaced by hexadecimal numbers. So in today's latest computers, the memory representation or memory addresses are generally represented using hexadecimal number system. While binary number system consists of total 2 digits, 0 and 1. And this binary is actually also known as computer's language. Computer only understands 0 and 1 language, that is binary language. So anything that is entered in computer is ultimately converted into binary number. So in today's discussion, we are going to convert an octal number to its respective binary number. So there are two techniques that you can follow for this type of conversion. We have an indirect method and also a direct method. It's up to you. Whatever method is easy or convenient for you, you can apply that. I'm going to discuss both the techniques here and also will be applying examples using these techniques. So let's see the indirect method for converting an octal number to binary number. The techniques says it consists of 2 steps. The indirect method is a 2-step method. In first step, we have to convert the given octal number to its respective decimal number. And this conversion, octal to decimal, has already been covered in previous lecture. So you must know how we can convert an octal number to decimal number. So in first step, we have to convert the given octal number to its respective decimal number, and in second step, the decimal number is then converted into binary number. We have already discussed decimal to binary conversion in previous lectures. So this is an indirect method in which we use an intermediate number system to reach to the end results. First we have to convert the octal number to decimal number, and then the converted decimal number will be then converted into respective binary number. Both the steps have already been discussed in detail in previous lectures, but I will apply both these steps in this lecture also on few examples. So let's see how we can apply this indirect method on an example. Here you can see we are given an octal number 205, and we need to convert it to binary number. Here we are going to follow the indirect method. As the indirect method says, first the given octal number has to be converted to decimal number. And you must remember in previous lecture how we converted an octal number to decimal number. The method was every digit in the given octal number is multiplied with 8. The power of 8 starts with 0. The multiplication process starts from right to left for the integer part, and for the fractional part the multiplication process starts from left to right, and the power of 8 then becomes -1. But since here we are given a whole number, a complete number, an integer number, there is no fractional part in it. So our multiplication process here will start from right to left. The power of 8 will start from 0. So let's convert or apply the first step. We need to first convert this octal number into decimal number. So step 1, 205 is the given number, and we have to first convert it into octal number. So as I just said, the method to convert octal number is to multiply every digit with 8, while the power of 8 starts from 0. So 5 is multiplied by 8, the power of 8 is 0. 0 is multiplied by 8, the power of 8 is 1. And 2 is multiplied by 8, the power of 8 is 2. Here you can see the multiplication process moves from right to left. Now we clear the powers, and this is the result after clearing up the powers. After multiplying we get this result, and after adding up the multiplication products, the end result is 133. This 133 is a decimal number. So 205, which was an octal number, has now been converted to 133, which is a decimal number. So here the first step is completed. Now we have to move on to the next step. Keep in mind, this is not the end result, so don't stop here. You have to then perform the second step. The second step now says this decimal number which has been generated needs to be now converted into binary number. And what is the procedure to convert a decimal number into binary? We have already discussed that in previous lectures. The method is, if you are given an integer number, so you have to divide the number with 2 successively until the quotients and remainders become either 0 or 1. And if you are given a fractional part, so the fractional part is then repeatedly multiplied by 2 until the result becomes 0. So let's start the second step. 133 was the decimal number we just generated by converting an octal number to 205. So 133 is repeatedly divided by 2, as we are going to convert this decimal number to binary number. So 133 is divided by 2. The result is 66 as quotient and 1 as remainder. 66 is again divided by 2, and the result is 33 as quotient and 0 as remainder. 33 is again divided by 2, and the result is 16 as quotient and 1 as remainder. 16 is further divided by 2, and the result is 8 as quotient and 0 as remainder. 8 is again divided by 2, result is 4 as quotient and 0 as remainder. 4 is further divided by 2, the result is 2 as quotient and 0 as remainder. 2 is further divided by 2 and the result is 1 as quotient and 0 as remainder. Here you can see this 1, which is a quotient, is within the range of binary number system. So it cannot be further divided by 2. So here our divisioning comes to an end. And as you know how we need to write the answer? In bottom up manner. So 133, which was a generated decimal number, its respective binary number is, first you have to write the bottom numbers. Bottom numbers are 1 and 0. So here you can see 1 and 0 are two first digits. And then you have to write the topmost numbers that include 3 zeros. Here you can see the 3 zeros, and then 101. Here you can see 101. So ultimately we have completed this conversion process. 205, which was an octal number, it was first converted to decimal number, and then that decimal number was converted to binary number. So how you will write the answer? This is how you can write the answer. 205, the given octal number, its binary equivalent is 100000101. I hope this indirect method must be clear to you. Now let's proceed to the other method. We have done indirect method. So now is the time to discuss the direct method, which is quite simple one. But again, it is up to you. Whatever method is easy for you, you can apply that method. The direct method says that every digit within the octal number is divided in groups of 3 binary bits. Binary bits, that means zeros or ones. If you remember, I have mentioned the number system relationship chart in first lecture, in which we have seen an octal number is equivalent to 3 binary digits, while a hexadecimal number is equivalent to 4 binary digits. So here the given octal number will be grouped in 3 binary digits. So if any group contains less than 3 bits, if the group is not complete, so you can add extra zeros towards the left of the group in order to complete 3 bits group. And then at the end we have to merge all the given or converted bits, and the result will be a binary number. This is a little tricky but an easy one. How you can do it? First you need to convert every digit in the given octal number in group of 3 bits. If any group contains less number of bits, so you can add zeros, respective number of zeros, towards the left side of the group in order to complete the 3 bits group. And at the end, all the bits will be combined together and result will be a binary number. Let's see with few examples how we can apply this direct method. Here you can see we are given an octal number 540. and we have to convert it into binary number using direct method. So direct method says every digit means 5 is treated separately, 4 will be treated separately, and 0 will be treated separately. So every digit will be divided or split in group of 3 bits. Why 3? Because octal generally forms 3 bits in binary conversion. So let's see how we can do it. 540 is the given number, so we split every digit like this. 5 separately, 4 separate, and 0 separate. And then we have to divide, or we have to split this every digit in 3 groups of binary digits. So you can see, as you know, this is how we can form binary formation. You cannot directly write 2 3 times. You have to generate powers of 2 in 3 group. So we have written 2 3 times, but every 2 carries a power. So first 2 carries power 0. As you know, the power starts from 0. Second 2 carries power 1, and third 2 carries power 2. Now you have to see when we clear up the powers. So our result would be 2 raised to power 2 is 4, 2 raised to power 2, 2 raised to power 1 is 2, and 2 raised to power 0 is 1. That collectively makes, if you add up all of them, that will make 7. But the number given is 5. That means some of the bits in this group will be off and some will on in order to generate 5. So how you can do it? If you see, if we can add 4 plus 1, so that will generate 5. That means we can off this 2, central 2 raised to power 1, we can keep it off. So how we'll write it? We need to switch on only the first and third bit, while we do not need the second bit, so we can keep it off. So ultimately 101 will be the conversion for 5. This is how you do it. Here you can see 101 we have just converted. A group of 3 is generated, and this is equal to, this group of 3 is equal to 5 in octal number system. Second number, as you can see, is 4. So here you can see 4 is the last number here. So if we only switch on the last number and keep off the first 2, so it will generate 100. That is equal to 4. And then the last digit is 0. 0 means no bit should be on. All the bits should be off in order to generate a 0 bit. So here you can see we generated a group of 3 zeros to generate a digit 0 in octal number. In next step, we need to merge or combine all these groups. So the answer would be like this. 540 in base 8 is equal to, we need to write 5, a group of 3 for 5 first. So 101 will be first written here. 101 you can see here. This is the first group, 101. Then for 4 it was 100. So for 4 it was here 100, and last is 0 3 zeros Here you can see the 3 last zeros. So this is how the direct method works. You need to split every digit in the given octal number in group of 3 binary digits. How we can group the 3 binary digits? You have seen the method. Start the 3 binary numbers with power 0. So it will lead you to just 3 binary digits starting from 2 raised to power 0, then 2 raised to power 1, and then 2 raised to power 2. So whatever bits generate the required number, keep that on, and whatever is not required, keep that bit off. So ultimately we combine all the bits, binary bits, and it is the resultant binary number. So this is how the direct method for octal to binary number system works. Let's see another example using direct method so you can have a clear idea how you can do it. Here you can see we are given an octal number 1364. So what is the method? Every bit, that means 1 is treated separately, 3 will be treated separately, 6 will be treated separately, and 4 will be splitted separately. So every bit in the given octal number, every digit in the given octal number will be divided in groups of 3 binary digits. So how we can do it? This is the given number and we split it this way. So you can easily generate the required sequence. So this is the sequence for every digit. So just first write these 3 binary digits group. So you can easily then form which number must be switched off and which should be switch on. So in order to generate 1, so this 2 raised to power 2, 2 raised to power 1 and 2 raised to power 0 is ultimately equal to 4, 2 and 1. That if you add all of them, so it will generate number 7. But we are not required number 7. We require what? 1. So where we can get 1? If we switch on the first bit, we will get 1 and the remaining of the bits will switch on. So how you can write it? Switch on the first bit and switch off the 2 last bits. Similarly for 3, you can see if we add first and second bit, so we will get 3, while the third bit needs to remain off. So how you can do it? 1, 1 and the last bit remains off. A group of 3 binary bits. Similarly for 6, you can see how we can get 6. If we add 4 with 2, we will get 6. That means second and last bits required to be switched on, while the first one should be switched off. It is not required. So first is switched off while the other 2 are switched on, this way. While the last is 4. So here you can see the last bit generates 4. So only last bit is required to be switched on while the first 2 is switched off. So here you can off the first 2 bit and the last bit is switched on. So this is how we convert it. 0, 0, 1, here you can see this is the conversion for 1. 0, 1, 1, here you can see is the conversion for 3, and 1, 0, 1, 1, 0 is the conversion for 6, and 1, 0, 0 is the conversion for 4. Here I have written 1, you can see it. I have written 1 here, but due to this line you cannot see it, it is not clearly visible. but I have already written 1 here. So this is how you can convert octal number to binary number using this direct technique. If you practice it more, it will be easy for you to understand more clearly. I hope the direct method must be clear to you now. How you write the answer? We need to group up all the numbers. All these numbers are grouped together. So 1, 3, 6, 4. For 1 we have 0, 0, 1. Here you can see for 1 it is 0, 0, 1. For 3 it is 0, 1, 1. For 3 it is, you can see, 0, 1, 1. For 6 it is 1, 1, 0. It is 1, 1, 0 here, and for 4 it is 1, 0, 0 here you can see. So we have merged all the answers. But keep in mind, you can also omit the first 2 zeros as they do not lead to any result. So these first 2 zeros can also be omitted. If you want to write it, you can, but since it cannot or it doesn't make any change in the answer, so you can avoid or you can omit it and directly start from first 1. So you can also write the answer as 1, 0, then 4 times 1, and then 0, 1, 0, 0. So you can also write it. We have avoided or omitted the last 2 zeros. So zeros towards the left can be avoided, but zeros towards the right cannot be skipped. Keep in mind. So this is also correct, and this one is also correct. If you convert it to again octal number, reverse conversion, so you will ultimately get this number 1364, both from this and from this. Now if you are given an octal number with a fractional part, so how you will convert it to binary fraction? So again we are going to follow both the techniques, the direct method and the indirect method. The indirect method, as you know, we have to multiply the fractional part successively by 2, and for the direct method we have to split every digit within the fractional part in group of 3, the way we have done it for the integer part. So the rule or the method is mentioned here. So you have to convert every digit in octal number or octal fraction in group of 3 bits, and if some group contains less number, you can add extra zeros towards the left. Keep in mind, towards the left, as adding zeros towards the left doesn't change the result, in order to complete the group. And then the decimal point, keep in mind that the decimal point stays at its place the way it was in octal number. You cannot change the position of the decimal point. And then we merge all the bits, and that is the resultant binary number. Same technique we just followed. You have to follow it for the fractional part as well, but do not change the position of the decimal point. So here we apply this rule on the given example. 0.73 is given octal fraction, and we have to convert it into binary number. So how we can do it? This is the given number. Every digit is written separately, as we have to treat every digit individually. So first we have to split every digit in group of 3 binary digits. So this is how we just performed in previous slide. Here you can see the point stays at its place. You cannot change the position of the decimal point, as I have mentioned it in the rule. So 0 would generate if we switch off all the bits. So all the bits would, if kept 0, would generate ultimately a 0. So this will be a group of 3. And then 7, as you know how we attempted 7, 2 raised to power 2 is 4, 2 raised to power 1 is 2, and 2 raised to power 0 is 1. That collectively makes 7. That means all the bits need to be switched on. So all the bits needs to be switched on. And then is 3. Here you can see if we add first and second bit, that will generate 3, while if we switch off the last bit, that will completely generate octal 3. So here you can write 0, 1, 1 this way. So the result is this: zeros for the integer part 0, the decimal part stays at its place, as you can see, and then for 7 we have just generated triple 1, and for 3 we generated 0, 1, 1. Now we merge all the binary fractions. So the answer is 0.73 in base 8 is equal to point stays at its place. So here you can see you have generated 3 zeros, but you do not need to write 3 zeros, that it doesn't change the answer. And I just said towards the left, zeros towards the left doesn't change the result. So 1 0 is enough. And then decimal at its place as it was in the original octal number, and then 3 ones. Here you can see 0, 1, 1, the last number, which you can see here, 0, 1, 1. So this is how you can apply the direct method on the fractions as well. We are given, let's see another example for the fractional part. So we are given an octal fraction 0.536, and we have to convert it into binary fraction. So how you can do it? Simple, direct way. I'm going to apply the indirect method as well in the coming slide. So the direct method, you have to split all the digits given in the given octal number and generate its 3 bits binary sequence. This is how it is generated: 0, 0, 0, all zeros, point stays at its place. And how you can generate 5? If you switch off the central bit and switch on the first and last bit, it will generate 5. 2 raised to power 2 is 4, and 2 raised to power 0 is 1. So 4 plus 1 is 5. First 2 is switched on while the central is off. 3 generates from first 2 bits. 2 raised to power 1 is 2, and 2 raised to power 0 is 1. That makes 3. So it will lead to first 2 switch on and last one as switch off. Then is 6. So 4, 2 raised to power 2 is 4, plus 2 raised to power 1 is 2. 4 plus 2 is 6. So we need to switch off the first bit and switch on the last 2 bits. So when we merge all these, the result will be a binary number. So this is how we have generated the answers. You can see similar answers are generated, and when we merge all of them, the resultant is the binary number. 1 0 is enough. No need to add 3 zeros, though you can add it, but it is not required as it will not change the result. So 0.536 in base 8 is equal to 0.101011110 in base 2. So similar method as we followed for the integer part, the same method you have to follow for the fractional part. This is the direct method. Now let's see how we can apply the indirect method on octal fractions. Now we apply the indirect technique to the fractional part. We are given an octal number 0.73, and we have to convert it into binary number. We have just converted the same 0.73 using direct method. So now we are applying the indirect method on the same example. So you can compare both the results from both the methods. So the indirect method says it has 2 steps. In first step, you have to convert the given octal number into decimal number. And in second step, the converted decimal number will be then further convert it to binary number. So how you can convert an octal number to decimal number? You have to multiply every digit with 8. For the integer part, the power of 8 starts with 0, and for the fractional part, the power of 8 starts with -1. For the integer part, the multiplication process starts from right to left, and for the fractional part, the multiplication process starts from left to right. So this is how we do it. In step 1, 0.73 is the given number. So we multiply the numbers like this. The integer part is multiplied by 8, and the power of 8 is 0. Here you can see. The fractional part, point is replaced with digit plus. Why digit plus? Because the fractional part will ultimately generate decimal points. So we need not to have further decimal points. So you can replace the decimal point with symbol plus. So first digit in the fractional part is 7. It is multiplied by 8. The power of 8, as you can see, is -1. Next digit is 3. It is multiplied by 8, and the power of 8 is -2. So multiplication process for the fractional part goes from left to right, and for the integer part it goes from right to left, or simply you can say you can start the multiplication process right from this decimal point. So one will lead you towards right to left, and other part will lead you from left to right. So after clearing up the powers, this is the answer, and we divide the given equations. If we divide them, 1 by 8 and 1 by 64, 8 raised to power -1, as you can see, is actually 1 by 8, and 8 raised to power -2 is actually 1 by 64. So after dividing, this is the answer. 1 by 8 is equal to 0.125, and 1 by 64 is equal to 0.015625. After multiplication, these are the results, and when we add up these products, the answer is 0.921875. But keep in mind, this is a decimal number. As you can see, all the digits or majority of the digits are not within the range of binary number. So this is a decimal number. 0.73 in base 8 is equal to 0.921875 in base 10. This is the first step. Now in second step, we need to convert this decimal number in base 2 or binary number. And what is the method to convert a decimal number to binary number? We need to multiply the decimal fraction with 2 repeatedly until you get zeros at the end. So let's start the step 2. This is the decimal number. We multiplied the given decimal number with 8, and the result is 1.8437. You need to store the integer part and multiply the fractional part again. So again we multiply 0.84375 with 2, and the result is 1.6875. 1 is again stored, and the fractional part 0.6875 is again multiplied by 2, and the result is 1.375. Again the integer part is stored and fractional part is multiplied again. So 0.375 is multiplied by 2. The result is 0.75. 0 is the integer part, it is stored, and 0.75 is again multiplied by 2. The result is 1.5. The integer part 1 is stored, and 0.5 is again multiplied by 2. The result is 1.0. It is stored. 1 is the integer part, it is stored, and the fractional part is 0. That means this is the end of the multiplication process. As if you multiply 0 with 2 again, so you will get zeros. So how you need to write the answer? You know, from top down manner. So 0.921875 in base 10 is equal to point stays at its place. Here you can see the decimal point is at its place. We have not changed the decimal point, but rest of the conversion starting from top to bottom, 1 1 1 0 1 1, starting from top to bottom. Collectively we write the answer as 0.73. This was the given problem, 0.73. it is converted ultimately or indirectly into binary number, and the binary number, converted binary number, is 0.111011. So this is how you can apply both the techniques, direct and indirect techniques, on the fractional numbers as well. So now we combine both the parts. We are given a complete octal number having an integer part and a fractional part, and we need to convert it into binary number. So you can use any method, either direct or indirect, to perform this type of conversion. So 352.563 is the given number. We are applying a direct technique. We need to divide every digit in the given octal number in group of 3 binary bits. So this is how we write the binary bits. Point stays at its place. Here you can see you cannot change the point, the place of the decimal point. So how 3 is generated? If we switch on the first 2 bits and switch off the last bit, we will get 3. So 110 will generate 3. How 5 is generated? If we switch on the last bit, switch off the central and switch on the first bit, it will generate 5. As 2 raised to power 2 is 4 and 2 raised to power 1 is 2 raised to power 0 is 1. 4 plus 1 is 5. This is how it is generated. How we can generate now 2? 2 raised to power 1 is 2. So switch on the central bit and switch off the 2 bits. Then points remains at its place. And then 5. How you can generate 5? 2 raised to power 2 is 4 and 2 raised to power 0 is 1. So 4 plus 1 is 5. So switch on these 2 bits and switch off the remaining bit. So next is 6. How you can generate 6? 2 raised to power 2 is 4 and 2 raised to power 1 is 2. So 4 plus 2 is 6. That means last 2 bits are switched on while first is switched off. How you can generate now 3? 2 raised to power 1 is 2, 2 raised to power 0 is 1. So 2 plus 1 is 3. That means first 2 bits are on while the last bit needs to be switched off. So this is how we convert them. The answer remains the same. We merge all the answers. Point remains at its place. Do not change the decimal place of or the position of the decimal point. So 352.563 is ultimately equal to, starting from the very left, 011. You need to write the answer for 3 first. So here you can see 011, but I have not written the first 0. As I just said, the left hand side zeros, you can omit them. So I have taken the 2 ones from there only, but you can write 0 with it if you want, but since it doesn't change the result or it doesn't bring any impact on the answer, so you can omit it. Then is 101, 101. Here you can see 101, and then is 0, 1 0 0 1 0, and then is the decimal point. Decimal point is at its place. Then 101, 101. Here you can see. Then is 110, 110. You can see here, and last bits are 0, 1 1 0 1 1 are here. So this is how we have converted the given complete octal number into binary number using direct method. Another example is here 41.10. It is a complete number having integer part and a fractional part, and you have to convert it into binary number. So using the indirect method, how you can do it? We have to first convert this octal number to binary number. So how you can do it? For octal to decimal number, we need to multiply every digit with 8. The power of 8 starts from 0 for the integer part, and the power of it starts with -1 for the fractional part. The multiplication process for the integer parts moves from right to left, and for the fractional part it moves from left to right. So this is how we do it. Here you can see 1 is the first digit in decimal part, so it is multiplied by 8. The power of 8 is 0. 4 is the second number in the digit, in the integer part. It is multiplied by 8 and the power of 8 is 1. We replace the point with plus. 1 is the first point. 1 is the first digit in the fractional part. It is multiplied by 8 and the power of 8 is minus 1. 0 is the second digit. The power of 0 is multiplied by 8. The power of 8 is minus 2. After clearing up the powers, these are the results. So 8 raised to power minus 1 is 8. 8 raised to power 1 is 8 and 8 raised to power 0 is 1. While 8 raised to power minus 1 is 1 by 8 actually, and 8 raised to power minus 2 is 1 by 64. So after clearing the multiplications and divisions, these are the results. 4 into 8 is 32. This is the answer. 1 into 1 is 1, and then 1 by 8 is 1 is divided by 8 and the result is 0.125. 1 by 64, the result is 0.15625. So we need to now first multiply these products. So after multiplication, this is the result and we add up the products. The answer is 33.125, but this is a decimal number. 41.10 is converted to 33.125 in a decimal number system. Now in second step, we need to convert this given decimal number in binary number. So how you can do it? Decimal to binary conversion, the integer part is divided by 2 while the fractional part is multiplied by 2. So let's first convert the integer part. 33 is the integer part. We divide 33 by 2 and the result is 16 as quotient and 1 as remainder. 16 is further divided by 2 and the result is 8 as quotient and 0 as remainder. 8 is further divided by 2. The result is 4 as quotient and 0 as remainder. 4 is further divided by 2 and the result is 2 as quotient and 0 as remainder. 2 is then again divided by 2 and the result is 1 as quotient and 0 as remainder. So here you can see the quotient 1 is within the range of binary number system and it cannot be further divided by 2. So how you can write the answer? From bottom up manner, but before writing the answer we need to convert the fractional part. Fractional part is 0.125 and how we can convert it? You need to multiply this fractional part repeatedly by 2. So 0.125 is multiplied by 2. The answer is 0.25. We need to store this 0. This is an integer part and multiply the fractional part again. So 0.25 is again multiplied by 2. The answer is 0.5. Store this integer part and multiply the fractional part again. 0.5 is again multiplied by 2. The answer is 1.0. Store the integer part and the fractional part is 0. That means our multiplication also stops here. So we need to write the answer in top-down manner. So compile the answer for 33. We need to write the divisioning result for 33. And for 0.125, we need to write the multiplication results. So for 33, you can see we have written from starting from bottom up 1 0 1 0 here you can see, and then 3 zeros, you can see 3 zeros, and last one here. Then decimal point at its place. Here you can see the decimal point at its place. 0.125 is written in top-down manner. So top-down manner, that means first is 0. First is 0 here you can see. Next is also 0. Next is also 0. And last is 1. You can see here 0, 0, 1. So it is base 2. So collectively we write the answer. 41.10 in base 8 is equal to 10001.001 in base 2. I hope both the methods should be now clear to you. So we have completed the octal to binary conversion. we discussed two techniques, direct technique and indirect technique. For direct method, you need to convert every bit or every digit in the octal number in group of 3 binary bits. How we can do it? We have seen the examples. And for the indirect, and at the end you need to combine all the generated groups, binary groups. And for the indirect method, you need to first convert the octal number to decimal number, and then the decimal number is then converted to binary number. So whatever method is easy for you, you can use that method and complete this assignment. Assignment will be uploaded on KCMS and you need to submit it within due date. You are not required to attempt both the methods. You can convert these octal numbers using any one method. Whatever method is suitable for you, whatever method is easy for you, you can attempt that or you can use that technique. So do not need to use both the techniques. I hope this all must be clear to you. That is all for now. In today's discussion, we continued our previous discussion from previous lecture where we were converted octal number system to decimal number system, and today we converted octal number system to binary number system. We have seen different techniques how you can perform this type of conversion, and you can apply or use any technique you want to. Both the techniques will result same answers. In next lecture, we will continue our octal number system conversion and perform octal to hexadecimal number system conversion. That is again an interesting conversion. So we will be doing that in the coming lecture. I hope things must be clear to you. That's all for now. I thank you all.